Overview Part 1, Storage Elements and Analysis. Introduction to Sequential Circuits. Types of sequential circuits. Storage elements. Latches. Flip-flops. Sequential circuit analysis. State tables. State diagrams. Equivalent states. Moore and Mealy models. Part 2, Sequential Circuit Design. Introduction to Sequential Circuits. Inputs. Outputs. Combinational. Logic. A sequential circuit contains storage elements, latches or flip-flops. Combinational logic. Implements a multiple output switching function. Inputs are signals from the outside. Outputs are signals to the outside. Other inputs, state or present state, are signals from storage elements. The remaining outputs, next state, are inputs to storage elements. Storage elements. State. Next state. Introduction to sequential circuits. Combinatorial logic. Next state function. Next state equals F inputs, state. Output function, Mealy, outputs equals G inputs, state. Output function, Moore, outputs equals H state. Output function type depends on specification and affects the design significantly. Inputs. Outputs. Combinational. Logic. Storage elements. State. Next state. Types of sequential circuits. Depends on the times at which storage elements observe their inputs, and storage elements change their state. Synchronous. Behavior defined from knowledge of its signals at discrete instances of time. Storage elements observe inputs and can change state only in relation to a timing signal, clock pulses from a clock. Asynchronous. Behavior defined from knowledge of inputs in any instant of time and the order in continuous time in which inputs change. If clock just regarded as another input, all circuits are asynchronous. Nevertheless, the synchronous abstraction makes complex designs tractable. Overview Part 1, Storage Elements and Analysis. Introduction to Sequential Circuits. Types of sequential circuits. Storage elements. Latches. Flip-flops. Sequential circuit analysis. State tables. State diagrams. Equivalent states. Moore and Mealy models. Part 2, Sequential Circuit Design. Basic, NAND, R latch. Cross-coupling two NAND gates gives the SR latch, which has the time sequence behavior. S equals 0, R equals 0 is forbidden as input pattern. S, set. Q, R, reset. Time. R, S, Q, comment. 1. Stored state unknown. Set Q to 1. Now Q remembers 1. Reset Q to 0. 1. 1. 1. Now Q remembers 0. 1. 1. Both go high. 1. 1. Unstable, basic, NOR, S, R latch. Cross-coupling two NOR gates gives the S, R latch, which has the time sequence behavior. S, set. R, reset. Q, R, S, Q, comment. Stored state unknown. 1. Set Q to 1. Now Q remembers 1. Reset Q to 0. Now Q remembers 0. Both go low. Unstable. Time, clock test, R latch. Adding two NAND gates to the basic S/R NAND latch gives the clocked S/R latch. Has the time sequence behavior similar to the basic S/R latch, except that the S and R inputs are only observed when the line C is high. C means control or clock. S, R, Q, C. Clocked S/R latch, continued. The clocked S/R latch can be described by a table. The table describes what happens after the clock, at time t+1, based on current inputs, S, R, and current state Qt. S, R, Q, C, D latch. Adding an inverter to the S/R latch gives the D latch. Note that there are no indeterminate states. D, Q, C, Q, D, Qt+1. Comment. No change. 1. Set Q. Clear Q. No change. C, D, Q. Flip-flops. The latch timing problem. Master-slave flip-flop. Edge-triggered flip-flop. Standard symbols for storage elements. Direct inputs to flip-flops. The latch timing problem. In a sequential circuit, paths may exist through combinational logic. From one storage element to another. From a storage element back to the same storage element. The combinational logic between a latch output and a latch input may be as simple as an interconnect. For a clock D latch, the output Q depends on the input D whenever the clock input C has value 1. The latch timing problem, continued. Consider the following circuit. Suppose that initially Y equals 0. As long as C equals 1, the value of Y continues to change. The changes are based on the delay present on the loop through the connection from Y back to Y. This behavior is clearly unacceptable. Desired behavior, Y changes only once per clock pulse. C, D, Q, Y. Clock, clock, Y. The latch timing problem, continued. A solution to the latch timing problem is to break the closed path from Y to Y within the storage element. The commonly used path-breaking solutions replace the clock D latch with a master-slave flip-flop, an edge-triggered flip-flop, a master-slave flip-flop. Consists of two clocked S/R latches in series with the clock on the second latch inverted. The input is observed by the first latch with C equals 1. The output is changed by the second latch with C equals 0. The path from input to output is broken by the difference in clocking values, C equals 1 and C equals 0. The behavior demonstrated by the example with D driven by Y given previously is prevented since the clock must change from 1 to 0 before a change in Y based on D can occur. C, S, R, Q. Flip-flop problem. The change in the flip-flop output is delayed by the pulse width, which makes the circuit slower, or S and or R are permitted to change while C equals 1. Suppose Q equals 0 and S goes to 1 and then back to 0 with R remaining at 0. The master latch sets to 1. A1 is transferred to the slave. Suppose Q equals 0 and S goes to 1 and back to 0 and R goes to 1 and back to 0. The master latch sets and then resets. A0 is transferred to the slave. This behavior is called one's catching. Flip-flop solution use edge triggering instead of master-slave. An edge-triggered flip-flop ignores the pulse while it is at a constant level and triggers only during a transition of the clock signal. Edge-triggered flip-flops can be built directly at the electronic circuit level, or a master-slave D flip-flop which also exhibits edge-triggered behavior can be used. Edge-triggered D flip-flop. The edge-triggered D flip-flop is the same as the master-slave D flip-flop. It can be formed by replacing the first clocked SR latch with a clocked D latch, or adding a D input and inverter to a master-slave SR flip-flop. The delay of the SR master-slave flip-flop can be avoided since the one's catching behavior is not present with D replacing S and R inputs. The change of the D flip-flop output is associated with the negative edge at the end of the pulse. It is called a negative edge-triggered flip-flop. C S R Q D positive edge-triggered D flip-flop. Formed by adding inverter to clock input. Q changes to the value on D applied at the positive clock edge within timing constraints to be specified. Our choice is the standard flip-flop for most sequential circuits. C S R Q D. Standard symbols for storage elements. Master-slave, postponed output indicators. Edge-triggered, dynamic indicator. A. Latches. S. R. Senior. D. C. D with one control. B. Master-slave flip-flops. Trigger D. Triggered senior. C. Edge-triggered flip-flops. D with zero control. Trigger D. Direct inputs. At power up or at reset, all or part of a sequential circuit usually is initialized to a known state before it begins operation. This initialization is often done outside of the clocked behavior of the circuit, i.e., asynchronously. Direct R and or S inputs that control the state of the latches within the flip-flops are used for this initialization. For the example flip-flop shown, 0 applied to R resets the flip-flop to the 0 state. 0 applied to S sets the flip-flop to the 1 state. D, C, S, R, Q. Overview Part 1, Storage Elements and Analysis. Introduction to Sequential Circuits. Types of sequential circuits. Storage elements. Latches. Flip-flops. Sequential circuit analysis. State tables. State diagrams. Equivalent states. Moore and Mealy models. Part 2, Sequential circuit design. Sequential circuit analysis. General model. Current state at time, t, is stored in an array of flip-flops. Next state at time, t plus 1, is a Boolean function of state and inputs. Outputs at time, t, are a Boolean function of state, t, and, sometimes, inputs, t. Inputs. Combinational. Logic. Outputs. Storage elements. CLK. State. Next. State. Example 1, from Figure 5.15, input, xt output, yt. State, a t, bt. What is the output function? What is the next state function? A, C, D, Q, Y, X, B, CP. Example 1, from Figure 5.15, continued. Boolean equations for the functions. A t plus 1 equals a txt plus bt, xt. bt plus 1 equals a t, xt. Yt equals xt, bt plus a t. X. D. Q. A. C. Q. A. Next state. D. Q. B. CP. C. Q. Y. Output. Example 1 from Figure 5.15, continued. where in time are inputs, outputs and states defined. 1. State table characteristics. State table, a multiple variable table with the following 4 sections. Present state, the values of the state variables for each allowed state. Input, the input combinations allowed. Next state, the value of the state at time, t+1, based on the present state and the input. Output, the value of the output as a function of the present state and, sometimes, the input. From the viewpoint of a truth table, the inputs are input, present state, and the outputs are output, next state. Example 1, state table, from figure 5.15. The state table can be filled in using the next state and output equations. A t+1 equals a txt plus b txt bt plus 1 equals a t x t y t equals x t b t plus a t. Present state. Input. Next state. Output. A t bt. xt. A t plus 1 bt plus 1. yt. 0 0. 0 0. 1. 0 1. 0 1. 1 1. 1 0. 1 0. 1 1. Example 1, alternate state table. Two-dimensional table that matches well to a K-map. Present state rows and input columns in gray code order. A t+1 equals a t, xt plus bt, xt. bt plus 1 equals a t, xt. yt equals x, t, bt plus a t. Present state. Next state. xt equals 0, xt equals 1. Output. xt equals 0, xt equals 1. A t bt. A t plus 1 bt plus 1 a t plus 1 bt plus 1. yt yt. 0 0. 0 0 0 1. 0 0. 0 1. 0 0 1 1. 1 0. 1 0. 1 1. 0 0 1 0. State diagrams. The sequential circuit function can be represented in graphical form as a state diagram with the following components. A circle with a state name in it for each state. A directed arc from the present state to the next state for each state transition. A label on each directed arc with the input values which causes the state transition, and a label on each circle with the output value produced, or on each directed arc with the output value produced. State diagrams label form, on circle with output included. State/output. More type output depends only on state. On directed arc with the output included. Input/output. Merely type output depends on state and input. Example 1, state diagram. AB 0 0 0 1 1 1 1 0 x equals 0 / y equals 1 x equals 1 / y equals 0 x equals 0 / y equals 0. Which type diagram gets confusing for large circuits? For small circuits, usually easier to understand than the state table. Type, Mealy. Equivalent state definitions. Two states are equivalent if their response for each possible input sequence is an identical output sequence. Alternatively, two states are equivalent if their outputs produced for each input symbol is identical and their next states for each input symbol are the same or equivalent. Equivalent state example 1 0 0 1 S 0 / 0 S 1 1 Text figure 5:17a. For states S3 and S2, the output for input 0 is 1 and input 1 is 0, and the next state for input 0 is S0 and for input 1 is S2. By the alternative definition, states S3 and S2 are equivalent. Equivalent state example: 1 0 0 0 S0 S1 0 1. Replacing S3 and S2 by a single state gives state diagram. Examining the new diagram, states S1 and S2 are equivalent since their outputs for input 0 is 1 and input 1 is 0, and the next state for input 0 is S0 and for input 1 is S2. Replacing S1 and S2 by a single state gives state diagram. 0 0 S0 S1 1 0 0 1. Moore and Mealy models. Sequential circuits or sequential machines are also called finite state machines, FSMs. Two formal models exist. Moore model, named after E.F. Moore. Outputs are a function only of states, usually specified on the states. Mealy model, named after G. Mealy. Outputs are a function of inputs and states, usually specified on the state transition arcs. Moore and Mealy example diagrams. Mealy model state diagram maps inputs and state to outputs. Moore model state diagram maps states to outputs. 1. X equals 1 / Y equals 1. X equals 1 / Y equals 0. X equals 0 / Y equals 0. 1 0. 2 1. X equals 1. X equals 0. 0 0. Moore and Mealy example tables. Moore model state table maps state to outputs. Mealy model state table maps inputs and state to outputs. Present state. Next state. X equals 0, X equals 1. Output 0 1 1 0 2 2. Present state. Next state. X equals 0, X equals 1. Output 0 1 0 0 1. Mixed Moore and Mealy outputs. In real designs, some outputs may be Moore type and other outputs may be Mealy type. Example, figure 5:17. They can be modified to illustrate this. State 00, Moore. States 01, 10, and 11, Mealy. Simplifies output specification. 10, 11, 10, 01, 000, 01, 1. Example 2, sequential circuit analysis. Clock. Reset. D. Q. C. R. A. B. Z. Logic diagram. Example 2, flip-flop input equations. Variables. Inputs, none. Outputs, Z. State variables, A, B, C. Initialization, reset to 0, 0, 0. Equations. A t plus 1 equals Z equals. bt plus 1 equals. ct plus 1 equals. A t plus 1 equals bc. bt plus 1 equals bc plus bc. ct plus 1 equals ac. Z equals A. Example 2, state table X equals xt plus 1 ABC abc Z 0 0 0 0 0 1 0 1 0 0 0 0 0 0 1 0 1 0 011 100 101 110 111 ABC 001 010 011 100 000 010 010 100 Z 0000111. Example 2, state diagram. Which states are used? What is the function of the circuit? O, O, O. O, 1, 1. O, 1, no. O, 1. 100. 101. 110. 111. Reset. ABC. Only states reachable from the reset state O are used. O, 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 001, 01 no, 011, and 100. The circuit produces a 1 on Z after 4 clock periods and every 5 clock periods thereafter. 000, greater than 001, greater than 010, greater than 011, greater than 100, greater than 000, greater than 001, greater than 010, greater than 011, greater than 100. 11.